Welcome to 40th lecture in the course of Industrial Engineering and Operations Research. We are now discussing the operations research portion. I already delivered 9 lectures on linear programming. Now in this lecture, we will just solve some interesting exercise problems. So we'll go to first problem. Now this problem I have picked up for this purpose that it is sometimes some skill is needed to formulate a proper linear programming problem. Solving the linear programming problem is not difficult nowadays. Although I have told you basic concepts and using pen and paper and calculator, you can solve exercise problems, which is must. You should know the basic concepts. However, nowadays you can solve them easily using the MATLAB function, or you can use that in the Google. If you give that online LP solver, then you can be directed to many website. A to Z.com is also there. Many free packages are there where you can easily get the solution, and there are many other type of packages also available which you can purchase also. So solution is not a big problem, even if you solve the LP problem which may have about 500 variables and it may have about 1000 constraints. That can be easily solved with the help of computer following the same procedure, that simplex algorithm which has been taught you. So skill is actually nowadays in proper formulation of the problem. So I am giving as an example one problem that suppose you have to minimize absolute x plus absolute y plus 3 times absolute z subject to x plus 2y is smaller or equal to 10 and 2x plus 5z is equal to 60. Now how to solve this problem? This is not a linear programming problem because objective function is not a linear. Had it been x plus y plus 3z, it would have been a linear function, but this is absolute x, so this is not a linear function. Suppose you have, say somebody gives you that fx is equal to absolute x, okay. Now if you plot this function, so if x is positive, then it is like this here. If x is positive, it is like this, it passes through 0, and here it is also this thing, this is inclined 45 degree, this is also inclined by 45 degree, this is x and this is fx, okay. So you have got that type of function. Naturally it is not a linear function. If x is in the positive range, it is one line, in the negative x there is another line. So how to make that linear, it as a linear programming problem, so that easily you can solve with any available package or by your method of solving in the pen and paper. Now let us show how we can do that. So technique is that you have to convert it into linear function. So if we introduce variables a, b and c and they are positive, suppose mod something like mod x is always positive, so this is always positive, okay. So this is always positive, yes, this is always positive. Suppose, so I give that some constraint. I introduce a, b and c such that I say that variable a is always greater than x, mod x or mod x is smaller than a. Similarly, mod y is smaller or equal to b, and mod z is smaller or equal to c, okay. And then I say I am minimizing a plus b plus c. So if I minimize a plus b plus 3c, okay, that means I am minimizing x plus y plus 3z also, because x plus y plus 3z is smaller or equal to this one. So therefore we minimize a plus b plus 3c, and which are a, b, c are positive. So both we have to add constraints. Okay, so we have to say, now we have to add constraints. So what happens, because condition is that mod x should be smaller or equal to a, it implies that x is smaller or equal to a and x is also greater or equal to minus a. That means it lies between a and minus a. Same thing you have to do for y. Okay, so that means now this constraint is also linear. So I just have added linear constraints, and now objective function is also linear. So this is because suppose we say that x lies between minus a to a. So mod x will be smaller than a if you know x will lie between minus a to a. This is the reason I have shown it graphically here. Okay, so that means this amounts to, that means x should be smaller than a and x should be greater or equal to minus a. So that means it should be in that range. So this is what that we have said like that. So this is equal to this thing. So now suppose x is greater or equal to minus a, so it implies that x minus s is equal to minus a, where s is a surplus variable, r and s is also greater or equal to 0, you have to say. Otherwise s minus x is equal to a, because we can write like that, and x is, but x is unrestricted, you know, x can be positive, negative, both. So we can always say x is equal to x plus minus x minus, where we impose that x plus and x minus both greater or equal to 0. So both are positive quantity. So any real number can be represented as the difference of two real numbers, okay, two unrestricted real numbers. So the x is anything, it may be positive or negative, but x plus is always positive, x minus is always positive. So a real number can be represented as a difference of two positive real numbers. Okay, so this is I have done for x, and same thing you have to do for y. Okay, because y is smaller than this one b, so I am not explaining that together. So naturally your variables got increased, but now your problem has become proper. It had become a proper linear programming problem that minimize a plus b plus 3c, where a, b, c are positive things. Okay, and you have imposed the constraints, so that when you minimize a, b, c, naturally x plus y plus 3z will also get minimized. Okay, so that is the one problem. Okay, let us say that this type of problem, suppose you have fx is equal to maximum of 3x plus 4y comma 6x plus y. Now how to solve that type of thing? That we have got a function and we have linear problem. Fx is defined like that. Fx is maximum of two functions. That means for any particular value of x and y, you calculate 3x plus 4y also, you calculate 6x plus y also. Whichever is greater, that value has to be taken. So it is minimize fx, and subject to fx plus 2y smaller or equal to 7, 7x plus 9y greater or equal to 8, and let us say xy is greater than 0. How to solve that problem? This is also not LP problem, because in LP problem, in the objective function you need one function, but here are two functions. So we can define another variable theta. We can define theta, and that theta will be such that theta will be greater than 3x plus 4y also, and theta will be greater than 6x plus y also. So therefore, if I maximize theta, then naturally that you know that this also gets maximized. Okay, so this is a theta, so it is something like that. So we are maximizing. So theta is naturally greater than this one. So you so the above are two linear constraints we can introduce, and we can say that here our constraint is that minimize theta, because we have to minimize. So I can say minimize theta, but theta is always more than 3x plus 4y, and theta is always more than 6x plus y. Okay, So therefore naturally that means 3x plus 4y or 6x plus y should be smaller than theta. So if I make theta very small, then this function will be even smaller than that, or maybe that in the limiting case it can be equal. So that's how that I can do that type of thing. So like that, for many problems you can just change your objective function and you can do that. Here I had to introduce one extra variable theta. Now another thing, okay, again I am highlighting, I have been doing that. Suppose you have a free variable x, x is unrestricted, it is also called free variable. It can be replaced by x plus minus x minus, okay. That means x plus is also greater or equal to 0, x minus is also greater or equal to 0, both are greater or equal to 0, both are positive, and this one we can do that. So for example, suppose x is equal to actually minus 7. So it can be represented as this one. Suppose it is minus 7, x is equal to minus 7. Then it is basically, can be written as something like you can say 9 minus 16. Suppose x plus was 9 and x minus was 16, both are positive. So their difference will be minus 7, okay. So that means this is just one illustration. So any variable which is unrestricted can be written as the difference of two variables. That means you have introduced one extra variable, okay. Instead of one, now there are two variables. But another way is that to eliminate it somehow, that suppose x is unrestricted and you have x plus y is equal to 5. So you can say x is equal to 5 minus y. Now y may be greater or equal to 0. So another way is the replacement also. So for example, if you have minimized, now suppose consider the another problem, that suppose you have minimized 3x plus 2y plus 4z, okay, and subject to x plus y plus z is equal to 10, x plus 2y is equal to 7. Two equations have been given, and then there are variable bounds, that 0 is smaller than x, is smaller than 5, 0 is smaller than y, y is smaller than 8, and z lies between 0 and 10, like that. So now what to do that, how to make it write in proper linear programming form? So write the last three constraints as x plus s1 is equal to 5, 0 is smaller than x, 0 is smaller than or equal to x, 0 is smaller than or equal to x means x greater or equal to 0. Similarly, 0 is smaller than equal to y means y greater than 0, and here it means z greater than 0. So naturally they are greater than 0, but x is also smaller than or equal to 5. So we can write x plus s1 is equal to 5, where s1 is called the slack variable, and I can write y is smaller than 8. Therefore y plus s2 is equal to 8, and z is smaller or equal to 10. So therefore z plus s3 is equal to 10, and we can say that x, y, z, s1, s2, s3 all are greater than 0. So this has become standard form. So you can eliminate this. Now this is not needed because I have written. So one constraint this, 2, 3, 4, 5. Okay. So that means we have written there are 5 constraints, and variable bounds are, that means all of them are in positive quadrant or first quadrant. Okay. So that is what the problem. Okay. So like that you can do. Now what I am telling that naturally the simplex method can be used for sometimes by solving the equation also. Suppose you want to solve that some equation, simultaneous equation. I am just giving x plus y plus 3z is equal to 10, z plus 2y is equal to 7, x plus 5y plus 16z is equal to 100. Suppose this type of equation is there. Okay. So 3 equations, 3 unknown. Okay. Now how to solve this type of equation? Such type of means 3 equations are there, 3 unknown. Okay, z plus 2y is equal to 7, x plus 5y plus 16z is equal to 100. How do you solve that? So, for solving Gauss elimination method and other methods are there. You can use Cramer's rule, you know that, but you can solve that if you have got an LP solver also. How you can solve that? Consider them as a constraints. They may be constraints, and you can say that maximize any variable. You can say suppose w is equal to something, and maybe x plus y, such that these are the constraints. So doesn't matter that w is equal to x plus y, these constraints have to be satisfied. There are 3 equations, full equality equations, and 3 unknowns. So naturally you will get value of x, y, z. Variable optimization variable can be anything. You can say maximize w is equal to x plus y, or simply say maximize w is equal to x also. No, doesn't matter. You put it there in the LP problem. You can do by hand in simplex table you make, and you do the operation. Naturally you will get solution. But here x, y, and z are unrestricted. Okay. So therefore you have to do little bit more. That means you have to say x has to be represented as x plus x minus. Similarly, y has to be represented y plus y minus. This much work has to be done. Okay, no doubt about that, that you have to say x plus. So therefore, in essence, you will have 6 variables, but you will have 3 constraints equation only, and now x plus and x minus all will be greater than 0. Then you will solve the LP problem. Then you will get the values of x plus x minus, y plus y minus, and from that you can find out the value of x, because x plus minus x minus is equal to basically x. It is basically equal to x. Okay. So this is how that it can be done. Okay. So this is also, these are the other applications of that LP you can do. Of course, we have to see that whether this method is efficient or not, but sometimes if you have got some LP package, you can use it like that. Okay. Now let me just help you for some multiple choice question on that. Now choose the correct option. In a minimization problem, the optimum function value came out to be 100. Suppose in a minimization, I wanted to minimize some objective function, I obtained that value as 100. If one of the design variables is constrained to be an integer, suppose I say no, this part one minimization problem may have say maybe 50 variables, but I say that 4th variable is always integer if I constraint. Earlier though no restriction was there, now I have put extra restriction. So the question is that the optimum value will be what? Will it be more than 100? Will it be less than 100? Will it be less or equal to 100? Will it be more or equal to 100? So you may give a pause to your video and maybe you can think, and then after that you can resume your video again and you can see its answer. So the question is that how we do that? It is based on very basic principle that if you put the constraint, then optimum value will not improve. It can only deteriorate. So what do mean deterioration here? It is a minimization problem. So if it is deteriorated, that means it will be more than 100 only. So I have now put a constraint, because earlier I was free to choose anything, but now I am telling no, you cannot change anything. This particular variable has to be integer only. So that means I am putting a constraint. I am telling that this particular value should be integer only. So therefore naturally my value will deteriorate. So therefore it should be more than 100. So is it the option is more than 100? No, but it may also happen that constraint may not affect that thing, because that constraint may be inactive. Maybe your naturally that solution is that where that variable becomes integer. So it can be 100 also. So correct option is more or equal to 100. It can be more than 100 or it can be equal to 100. So this is, so option is D, more or equal to 100. Again I am writing here why I am constraining it to be integer, which is extra constraint. hence solution will deteriorate. I was getting 100 as minimum, now I may not be able to get 100, surely I shall not get because there is a better solution of minimization. So this is what that I have written, that maybe you don't have to pay attention to these wordings. I am explaining here that now I may not be able to get 100, but I can also get 100. Okay, that means it is also possibility that I can get 100 also. Surely I shall not get less than 100. So this is what, okay, somehow less than sign got missed. Surely I shall not get less than 100, because if you get less than 100, that means you are improving. So putting a constraint doesn't improve the solution. Okay. Now I am just asking again basic question, that suppose a function f(x) is said to be strictly convex if for any two distinct points x1 and x2. x1 and x2 are 2 points. Okay, the x1 is basically vector. x1 may contain 2 coordinates, 3 coordinates, whatever is that thing. So we say that f lambda x1 plus 1 minus lambda x2 is smaller than lambda fx1 plus 1 minus lambda fx2. So the question is that between which values lambda lies. It is just a definition oriented question. This is the definition of a convex function, but you should know that what is lambda. So the answer is basically 0 and 1. That means lambda lies between 0 to 1, and this is the thing. If graphically I have to illustrate that, I can say, okay, I have got one point as x1 here, x1, and you have one point as x2 here, and then I can do like that, join any line. So that means all the points on that particular line must lie here. That means interpolated value, but not that outside, not that you even this much. Suppose you just draw a big straight line and you say that this point is outside the domain of set, that is possible. But what is that I am telling, that if you have got 2 points and if you join those points by line, then all, and if these 2 points are the end points, then every point will be in the set. So this is mathematically stated as f lambda x1 plus 1 minus lambda x2 is smaller or equal to lambda fx1 plus 1 minus lambda fx2. But here lambda, so this definition is incomplete. We have to add that 0 is smaller than lambda is smaller than 1. That is why the answer is 0 and 1. Now consider the problem of maximization of a function with a constraint gx greater than or equal to b. So if b is increased, then f is likely to increase or decrease. That is the question. So my thing is that I am maximizing the function. Okay, so I am maximizing the function, maximizing fx function. Now constraint is that gx is greater or equal to b. Okay, now b I am increasing. Suppose gx was, suppose b was 5. So my thing was that gx should be greater than 5. Now I increase, I say no, gx should be greater than 6. So which one is more tight constraint? Which one is more strict? Gx greater than 5 or gx greater than 6? Naturally gx greater than 6 is more strict, because when I said gx greater than 5, okay, that means gx is more than 5. Okay, but gx has to be more than 5. That means gx can be 5.5 also, it can be 6 also, it can be 7 also. So gx greater than 6 is contained in this. Suppose you just say that, okay, graphically you show that, suppose this is x and this is function g. Okay, suppose I say that gx 5. So suppose I say that this is 5 and I say that this is 6, this is 5. So if gx greater than 5, that means all the region here and here that contains gx greater than 6 also. But if I say gx is only greater than 6, then I am that means eliminating this region. So that means I am not allowed to take 5.5. So naturally gx greater than 6 is stricter. So I have increased the b. So therefore my optimization solution is likely to deteriorate. Okay. So it was a maximization problem. So therefore f is likely to decrease. Okay. It may not decrease also, it may be just equal, but it is likely to decrease. So objective function is likely to be decrease because you are making constraint stricter, more tight. Hence you cannot expect a better solution, but you can just expect equal solution. That is okay because constraint can be inactive also. Okay. Let us do that this problem. Suppose you say that maximize z is equal to x1 plus 2x2 plus 3x3 minus x4 subject to these are the three constraints x1 plus 2x2 plus 3x3 is equal to 15 and 2x1 plus x2 plus 5x3 is equal to 20, x1 plus 2x2 plus x3 plus x4 is equal to 10 and x1, x2, x3, x4 is equal to 0. You can solve this problem, but these are the by simplex method, but this is equality constraint. So you can use either two-phase method or you can use big M method. Okay. That means you have to introduce artificial variables here, that you have to say that plus R1 extra, which will become like a slack variable, plus R2 plus R3. But you have to say maximize this one, this thing, and you may have to say minus MR1 minus MR2 minus MR3, where R1, R2 are, where M is a very big number. So in the process of maximization, naturally that R1, R2, R3 will become 0 ultimately. So you have to do that like this because you are maximizing, therefore you subtract, that means you put a penalty type of thing, you say minus MR1 minus MR2 minus MR3 like that. So you solve by big M method, then you can get a solution. X1 is equal to this much, X2 is equal to this thing, you can solve yourself. X3 is equal to 15 by this one and X4 is equal to this one. And now you can actually do that. Okay, that you z is equal to, you can obtain z is equal to this much. Okay, so z is equal to basically 15 by 6, 2 into 15 by 6, 3 into 15 by 6. Okay, because you got the values and therefore 3, 2, 5, 6. So therefore this is 15. So we got z is equal to basically 15 and x4 is equal to 0 of course. So you got that this one. So now just see the first constraint. First constraint is satisfied, x1 plus 2x2. So therefore this constraint is active. Similarly, we can see that other constraints are also active because they have to be active. In fact, the equality constraints have to be active. There is no way out. If you are solving the LP problem, so they have to be active and they may have non-zero shadow price. Okay, that means their shadow price can be, that means shadow price means unit worth of the resource. So if a constraint is active, then its unit worth of resource can be either something or it can be of course 0 also, but if it is inactive, then it has to be necessarily 0. Okay. So I want to highlight that point, that if a constraint is active, that doesn't mean that its unit worth of resource will be non-zero. It can be 0 also. That is what this one. So anyway, now one more problem. Let us say maximize z is equal to x1 plus 2x2 such that 3x1 plus 2x2 is smaller or equal to 12 and x1 is equal to 2, x1 plus x2 greater than 8, and then you say minus x1 plus x2 greater or equal to 4 and x1 x2 greater than 0. So if we have done this type of problem, how do we do that, solve that thing? We can do that of course graphically, if two are this one. So let us say graphically, if I plot, this is equal to like that, this is x1, this is x2, and this is z is equal to x1 plus x2. So such that 3x1 plus 2x2 greater or equal to 12. Okay. So how should I draw that? Suppose I make a line 3x1 plus 2x2 is equal to 12. So that means at x1 axis, if x2 is 0, x1 is equal to 4. So at 4 I have made it like that, and here it is 6. Okay. So this is 6. Okay. So this is 6. Okay. So, this is 6 and I join these two lines. Okay. So, this is constraint is this one. So, it will come feasible region comes this side, but we also have x1 plus x2 greater or equal to 8. So, that means if I draw this line, so x1 is equal to 8 may be here and x2 is equal to 8 may be here. So, this line is x1 plus x2. So, it says that your feasible region has to be there. So, just see, if I see this constraint and this constraint, I can see that there is no feasible region, because this region is this way, that region is this way. So, therefore, this problem is infeasible. Naturally, there is no solution here, okay, because once moment you say that x1 plus x2 greater or equal to 8, naturally that it cannot be. This one is smaller than this one, 3x1 plus 2x2 is smaller than equal to 12, that is not possible, okay. So, this is x1 plus x2 greater or equal to 12 and this is 3x1 plus 2x2 is smaller than 12. So, that is why this is infeasible solution, but you can solve it by simplex method also. When you solve with the simplex method, then you will find out that you will not get finally any basic feasible solution, okay. That type of thing situation will come. So, you will come to know that, okay. Finally, let us see that one more problem before we conclude, okay. Maximize z is equal to 15x1 plus 25x2 such that 4x1 plus 6x2 is smaller or equal to 360, x1 is smaller than 60, x2 is smaller than 40, x1, x2 is greater or equal to 0. Now, if you solve it, you can solve it graphically or you can solve by simplex method. Just you can pause the video, you yourself can solve. You will see that solution is x1 is equal to 60 and x2 is equal to 0. So, what is the unit worth of resource corresponding to 4x1 plus 6x2 is smaller than 360? So, let us see that whether this constraint is active or inactive. So, therefore, we just go to left hand side 4x1 plus 6x2. Now, put the value x1 is equal to 60, x2 is equal to 0. So, 4 into 60 plus 66 into 0, that becomes 240. 240 is not equal to 360. That means 240 is naturally less than 360. So, the constraint, it is feasible, okay. That means fine, solution no problem, but it is not equal to 360. It is not a border case. So, therefore, the constraint is inactive. Therefore, shadow price will be 0. Shadow price will be 0. You do not have to do anything. So, that is all for today and thank you very much. We will continue about transportation problems later on, okay. Yes, thank you very much.